Astronomers secured the sharpest views yet of 3I Atlas, an interstellar comet sweeping into the inner solar system. Hubble revealed its vast coma, while Webb gathered spectra that hinted at something unusual in its chemistry. For a brief window, the releases came in rapid succession, each dataset drawing global attention. Then the rhythm broke. Just as the comet's envelope ballooned beyond 300,000 kilometers and ground observers reported a persistent green glow, the official updates stopped. No new Hubble images, no Webb spectra, no Gemini releases. The stream of data that had opened with such precision fell to silence. The agencies gave a technical reason. Solar geometry had forced both Hubble and Webb into blackout, with strict rules that prevent observations too close to the sun. The limits were long established, but the timing raised sharper questions. Why did the cadence of releases collapse so suddenly? Why did Oumuamua and Borisov trigger rapid-fire results while this comet, larger and more active, disappeared into silence? The odds of seeing even one interstellar object in a lifetime are vanishingly small. Missing answers now does not just mean a delay. It means losing a chance that may never come again, and leaving the truth about our cosmic neighborhood unresolved. The absence itself has become the anomaly. What are we not being told about this rare visitor? On July 21, 2025, Hubble recorded the sharpest images yet of 3I Atlas. The nucleus, no more than 5.6 kilometers across, was dwarfed by a coma that stretched outward nearly 350,000 kilometers. At that scale, the halo was a quarter the width of the Sun itself. Such rapid expansion at this distance from the Sun was unexpected. By August 6th, the James Webb Space Telescope trained its NIR SPEC instrument on the comet. The expectation was that high-resolution spectra and infrared imaging would reveal its composition with unprecedented detail, but instead of headline images, only technical notes surfaced. Analysts hinted at unusual readings, but the public saw no visuals, only a promise that the data were under review. For a target this rare, the absence of Webb's signature images stood out. In the same weeks, Gemini South confirmed the activity in visible light, while amateur astronomers reported something stranger. The comet glowed with a persistent green hue, brighter and more consistent than typical. For many comets, this tint comes and goes, often linked to diatomic carbon or cyanogen. But observers noted that the color lingered and seemed unusually intense. Alongside the green, sudden brightening events were recorded in photometry logs, the comet's magnitude rising and falling far more sharply than expected. Oumuamua and Borisov, the first two interstellar visitors, showed irregularities, but their data reached the public in a steady cadence. In contrast, 3I Atlas revealed early signs of something different. It was larger, brighter, chemically stranger, and accompanied by an information stream that was already beginning to thin. By late August, the official explanation for the silence emerged. Observations had been halted not by choice, but by geometry. Hubble's solar avoidance rules forbid any target within 50 degrees of the Sun. Webb enforces an even stricter limit of 85 degrees. As 3I Atlas advanced along its orbit, it slipped past both thresholds. The instruments were placed into an enforced blackout window, with mission planning software preventing further attempts. These rules are not negotiable. They exist to protect delicate optics and infrared sensors from permanent damage. A single exposure to direct sunlight could endanger years of work and billions of dollars in hardware. For the Space Telescope Science Institute, which schedules both observatories, the choice was never on the table. Once the comet crossed the line, the blackout became automatic. Yet the explanation raised its own questions. Oumuamua and Borisov had also passed through difficult observing geometries, yet their data reached the public in a far steadier rhythm. With 3I Atlas, the cadence collapsed almost overnight. The blackout, while technically valid, arrived at the exact moment when reports of a swollen coma, rapid brightening, and a green tint were peaking. The result was a silence that felt different. Not simply a gap dictated by engineering limits, but a pause that shielded information at the very point curiosity was highest. In the absence of new data, the official rules themselves began to look less like boundaries and more like a wall. Hints of something stranger had already circulated before the blackout took effect. According to unconfirmed notes from early spectra, Webb detected an unusually strong signal of carbon dioxide in the coma of 3I Atlas. While this remains unpublished and outside the peer-reviewed record, the whispers carried weight. Most comets in the inner solar system are dominated by water ice. At distances similar to 3I Atlas in late July, sublimating water vapor is expected to shape most of the coma's activity. Carbon dioxide normally plays a secondary role, detectable but weaker. In this case, the CO2 appeared to dominate, a pattern rarely if ever seen in local comets. At the same time, ground observers recorded the persistent green glow. The cause was likely diatomic carbon, a classic cometary signature, but its intensity and duration were unusual. In many comets, the green fades as the molecules are broken apart by sunlight. Here, the hue remained vivid for weeks, refusing to diminish. Cyanogen was also suggested as a contributor, but without spectra in the public domain, no firm conclusion was possible. If the whispers of CO2 dominance prove correct, the chemical picture becomes even stranger. A comet fresh from interstellar space, carrying a volatile balance unlike local examples, would challenge existing models. For some, the idea of an engineered volatile mix began to circulate, speculation that the object's chemistry looked less like the random signature of a natural fragment and more like a tuned profile. For now, the evidence remains fragmentary. But the chemistry of 3I Atlas may be the key to why it glows, why it brightens, and why it refuses to conform. By late August, the mystery of 3I Atlas deepened in the numbers themselves. Photometry logs from both professional observatories and amateurs began to scatter, producing results that did not align. Some measurements placed the comet at 1 magnitude of brightness, while others recorded values more than a full magnitude higher. A spread of this size cannot be explained by calibration alone. Differences in equipment and filters account for small deviations, but the sheer scale of disagreement suggested a target in rapid flux. Night to night, even hour to hour, 3I Atlas seemed to behave differently for each observer. The inconsistency hinted at something dynamic within the coma. Sudden outbursts of gas and dust could account for brief brightening, followed by fading as the cloud dispersed. But the rhythm did not match normal cometary behavior. Spikes appeared abruptly, lingered, then vanished without clear cause. Was this the signature of a comet unraveling, or something actively modulating the light we see? Some speculated that the nucleus itself was fragmenting, with pieces breaking free to briefly reflect more light before dispersing. Others suggested structural instability, with surface jets activating unpredictably as sunlight struck fresh volatile layers. Still others whispered about modulation, as though the light itself were being controlled or patterned in ways not typical of natural release. Whatever the mechanism, the light curve of 3I Atlas refused to settle into a predictable pattern. Instead, it became a scatter of contradictions, a signature of a body that seemed restless, unstable, or perhaps responsive to forces not yet understood. While ground observers struggled to make sense of the comet's erratic light, the silence from flagship telescopes grew more pronounced. The reason lies in the data pipeline itself. Every observation captured by Hubble or Webb enters a series of complex stages before reaching the public. First, raw signals are downlinked and tagged with spacecraft telemetry. Cosmic rays are scrubbed from the frames, detector quirks corrected, and background light subtracted. The data then pass through calibration routines, aligning them with known standards. For Webb, the process is even more elaborate, with multiple passes through infrared correction software before any spectrum is deemed science-ready. Once processed, the data do not immediately reach the public. Instead, they enter proprietary holds. 6 months is standard for Hubble, up to a year for Webb. This window allows principal investigators to analyze the material without being scooped by outside researchers. Some investigators release early, but many prefer to withhold until results are fully checked. Beyond the teams, multiple agencies review each dataset. NASA, ESA, and sometimes CSA all weigh in, examining not only the science but also legal and communications considerations. Only after this chain of approvals can headline images or spectra appear. But in a moment of heightened curiosity, should months of delay be accepted as caution or questioned as control? The result is a system designed for caution, not speed. Yet in the case of 3I Atlas, the blackout has created fertile ground for speculation. As the data creep through their pipeline at an institutional pace, the absence of immediate answers invites rumor, and every unexplained detail becomes a canvas for doubt. By the end of September, the blackout was no longer seen as a technical formality. Online forums and social media filled the silence with theories of their own. Some pointed to classified satellites, suggesting that military sensors had captured close-range images of 3I Atlas that would never be shared with the public. Others claimed that the blackout itself was deliberate, a tactic to manage headlines and prevent panic if the data contained something alarming. One camp pushed an even sharper line. According to them, the comet's chemistry, its erratic brightness, and its oversized coma all pointed to the same conclusion. 3I, Atlas was not a natural fragment. It was built, not born. The phrase spread quickly, tied to graphics and speculative threads claiming that the volatile mix seen in early spectra resembled deliberate design more than chance. Engagement spiked after Gemini South's September release, 10 times higher than typical cometary stories, then began to drift into conspiracy hashtags as the blackout stretched on. Algorithms rewarded the speculation. Each gap in the official record gave fuel to more elaborate interpretations, some suggesting the comet concealed a hollow core, others hinting at internal energy sources. The reality behind the scenes may have been slower and more methodical, but perception is its own force. The gap between official science and public interpretation widened with each passing week. What began as routine silence hardened into suspicion. And in that vacuum, rumors found their strongest gravity. The next opportunity to break the silence came not from Earth, but from Mars. On October 3, 2025, 3I Atlas passed within 0.19 astronomical units of the planet, a distance of about 28 million kilometers. In cosmic terms, it was a close approach, though still far too distant for sharp imagery. Mars orbiters turned their instruments toward the comet. The trace gas orbiter, best known for its surface mapping, attempted to capture brightness data. At this range, its camera could not resolve the nucleus, only a point of light against the background stars. Mars Reconnaissance Orbiter carried higher resolution optics, but even its capabilities reduced the nucleus to a blurred pixel. What the orbiters could provide was photometry. Measuring changes in the comet's brightness from another vantage point offered a critical check, especially while Earth's observatories remained locked out by solar geometry. The data pipelines for Mars missions are leaner than those of Webb or Hubble. Downlinks can reach Earth in days, not months, and results can circulate quickly among mission scientists. The Mars flyby did not promise detail. It promised coverage, a thread of continuity when the flagship observatories were silent. In a blackout window defined by geometry, the red planet briefly became the eyes of the world. The next critical milestone lay at the end of October. On the 29th and 30th, 3I Atlas swept through perihelion, its closest approach to the Sun at 1.36 astronomical units. The encounter was not a classic sun grazer, yet the heat and velocity placed the nucleus under severe stress. Perihelion is where comets often fracture or fade. For observers, it became the ultimate stress test. A smooth light curve rising and falling with the Sun's distance would suggest steady sublimation. Sharp, irregular jumps could point to outbursts or fragmentation events. The scatter in brightness from September gave reason to expect volatility. Geometry added another clue. The comet's anti-tail, the sunward-pointing spike of dust, was predicted to flip orientation as Earth's view shifted. Watching the spike emerge, rotate, and then fade would provide direct confirmation of orbital parameters and dust dynamics. Color changes were another key. Amateurs had tracked the persistent green tint. If it shifted or disappeared after perihelion, it could mean surface layers were depleted, exposing new chemistry beneath. By early December, elongation would widen again, allowing Hubble and Webb to resume observations. For many, this return marked the moment of truth. Would 3I Atlas survive intact, or would it emerge transformed, carrying answers to questions still unspoken? And if it does return, will the next images resolve the mystery or deepen it even further? By December, the record of 3I Atlas carried two competing narratives. The official version spoke of geometry, pipelines, and institutional caution. Observatories had obeyed their keep-out rules. Data were moving through calibration, and results would appear in due course. Nothing unusual, only the pace of science. The unofficial record told a different story. It highlighted the swollen coma, the scatter in light curves, the persistent green glow, and the whispers of carbon dioxide dominance. It emphasized the sudden blackout, the silence at the moment interest peaked, and the rumors that spread in the void. Between these versions lies a gap with real stakes. For astronomers, the comet represents a chance to test models of interstellar chemistry and the limits of cometary stability. For the public, it has become a test of trust, a measure of whether rare discoveries are shared, openly or filtered through layers of delay. And for those drawn to speculation, it raises a sharper possibility. If 3I Atlas carries signatures too strange to explain, what then? If its chemistry is tuned, if its light is modulated, if its structure is more than ice and dust, what does that mean for us? What if this visitor is not just passing through,